Hello from Germany. My name is Florian Wolling. I'm Research Associate and PhD candidate of the Ubiquitous Computing Lab at the University of Siegen. Together with my colleagues from the University of Freiburg, we had the idea of a novel approach for the detection of hand washing. So today I'm presenting WetTouch, touching ground in the wearable detection of hand washing using capacitive sensing. The detection of hand washing is not only relevant since the COVID-19 pandemic. Approximately 2.3% of all individuals are at some point affected by obsessive-compulsive disorders. More than half of the diagnosed people show washing or cleaning compulsions. Compulsive hand washing is done in an excessive, stereotypical and even robotic way. Cognitive behavioral therapy with exposure and reaction prevention is an effective treatment. The immediate intervention and treatment requires, however, the immediate detection of hand washing in daily routine. The computer-assisted assessment and therapy has the potential to reduce healthcare costs and to increase treatment efficiency for patients. The biggest challenge for technology is, however, to distinguish compulsory hand washing from other activities, such as a non-obsessive hand washing, eating, brushing teeth, etc. The detection of hand washing in general has already been subject to research. Mostly instrumented environments are applied to detect and monitor the hygienic behavior. They use sensor-equipped dispensers and sinks, or even analyze video recordings. In this way, for example, the gamified approach Germ Destroy is able to improve the average hand washing time and to decrease its perceived duration. There have also been approaches using wearable devices equipped with EMG or IMU sensors. With the pandemic, also commercial devices try to detect hand washing using microphones and IMUs. Hidden Markov models and artificial neural networks have been applied, but the reliable detection of hand washing is not yet guaranteed through these modalities. Consequently, a water-sensitive ring has been developed to directly detect water contact. However, with our method, we propose a novel sensing modality that enables both the reliable and comfortable hand washing detection at the wrist. When we talk about capacitive sensing, we first need to talk about capacitive coupling. A so-called capacitance is established between any conductive surfaces, and their different charging results in an electric field. In this way, natural capacitances form between any conductive objects as well as between objects and their environment. In turn, the environment is again connected to Earth ground, which is associated with a quasi-infinite pool of charges. It often serves as a neutral reference potential and return path all around the world. In capacitive sensing, a sensor capacitance is measured to capture the effect of interacting objects that couple to it and hence change its value. According to the capacitance of an ideal parallel plate capacitor, three parameters are leveraged: the electrode area A, their distance d, and the dielectric material between them epsilon. The effect of water on capacitive sensing can be observed well, for example, when raindrops fall on the touchscreen of a smartphone. These unwelcome ghost touches affect the interaction and are therefore mitigated. However, the dielectric properties of water can also be used for the interaction with water surfaces, as large touchscreen. Even different gestures can be distinguished by means of their different frequency response. We had the idea that wearing a capacitive sensor at the wrist might enable the detection of grounding and therefore the contact to water running from a tap. The sensor would have two electrodes, an excitation and a sensing electrode. The excitation electrode would be directly attached to the skin. It would be applied in transmit mode, which means that it would couple very strongly to the body and would virtually enlarge it to its entire surface. Applying a signal would induce a slight displacement current and hence modulate the body's electric field. The floating sensing electrode would be used to close a circuit and to measure the current flowing between the electrodes. We posit that touching a water jet would form a bypass towards the environmental ground. With its larger permittivity, it would improve the coupling and therefore increase the capacitance measurable at the device. To test and substantiate our hypothesis, we have developed a wearable sensing device. It consists of the AD7151 capacitance to digital converter, an ESP32 microcontroller which also provides Bluetooth and Wi-Fi connectivity, and a pair of electrodes. The electrodes are stacked with 1 cm distance to show only a weak coupling through the air gap. The calculated intrinsic capacitance is 800 femtofarad. However, attaching the device to the skin immediately increases the measured capacitance. Based on our hypothesis, we developed a physical model which might explain our observations. To simplify the circuit, the ideal capacitances are represented by their complex impedance Z. From the two-port perspective of the wearable sensor, the most relevant impedances are established between the two electrodes, the excitation electrode and the human body, the body and the receiver electrode, the receiver electrode and the environment, the air channel between the body and environment, and the water jet between the body and earth ground. Due to the close vicinity of the excitation electrode and the body surface, the impedance virtually resembles a short. This setting is called transmit mode, since the human body acts as an extension of the electrode surface. Consequently, the impedance is not considered in the resulting equivalent circuit. We first investigated the effect of different activities on the capacitive sensor. A single subject was grounding at the mains neutral wire, performing washing gestures with dry hands, and washing hands under a running tap. Apparently, the clusters of grounded and non-grounded activities clearly separate. Furthermore, the subject performed pertinent activities which might interfere. Washing gestures in a washpan that is not grounded, performing arbitrary gestures, contacting one foot with running water from the tap, and brushing teeth with a traditional non-electric toothbrush. Again, the grounded activity of contacting a food with the tap water is clearly separated from the non-grounded ones. However, the activity of brushing teeth lies somehow in between. Here, the close proximity of the sensor to the subject's head might cause a relative large capacitance. The other activities, in contrast, are performed with stretched arms and therefore the sensor farther away from the body. To show the repeatability of the measurements, two subjects repeated two of the experiments 5 times each. They performed washing gestures with dry hands and washing hands with tap water. Again, the two clusters of grounded and non-grounded activities are clearly separated. Wearable devices will enable the computer-assisted assessment and therapy of washing or cleaning compulsions. The immediate intervention and treatment in daily routine requires, however, the reliable detection of hand washing. With WetTouch, we have presented a novel sensing principle for the detection of hand washing. It uses capacitive sensing to distinguish grounded and non-grounded activities. The results are promising and show clearly separated clusters of hand washing with water from a running tap and other activities. We are currently designing an improved, smaller and more comfortable prototype. It will allow us to run a larger study with more subjects. We will also investigate more buildings and thus a larger diversity of water taps and supply pipes. Thank you for your interest in our research. I'm looking forward to answering your questions.